Hi everybody. So this one's going to be a doozy. But before we begin, say hi to Ava. Hi Ava. And say hi to Murphy. Hi Murphy. All right. So we're in section 3.1 and we're going to begin with trying to review or introduce, depending on who you are, function and function notation and different types of functions. So first of all, a function. And this is a loose interpretation of the actual definition. It's a rule on a set. Okay. A rule would be something like f of x is equal to 3x plus 4. It's an equation that you would know, or an operation or a process or a procedure. But in our world, 3x plus 4 would be the rule. F of x equals 3x plus 4. That's my dog's barking. So we got a rule on a set. Now that set is making reference to a domain. What numbers work in that function? All right. And where each element, and that's significant, each element of the domain, so every element of that set, has associated with it one and only one element in the range. Now that's a bit deceiving. The one and only one will need to be clarified in a little bit. As we work through it, we'll get back to that. Now, function notation. So you'll see this f with a set of parentheses. This does not mean multiplication. It's actually what it's implying is where you are along or in the domain, the set of the domain. So whatever value is here, you're going to go 3 times that value over here plus 4. Okay? So it really reads f of x or f at x. We should avoid the phrase f of x. It's what I learned a long time ago, but it really should read f at the value x. So it's a notation that indicates the place you are in the set that is the domain. So f at x is equal to 3 times x plus 4, or we just write 3x plus 4. All right. An example would be f at the value 2 is equal to 3 times 2 plus 4. Well, f at 2 is 10, because 3 times 2 is 6, plus 4, we get 10. You could say, so f at 2 is 10, or it's the ordered pair 2, 10. All right. Now, we have ways to tell if relationships are functions, and we can graph them, and we have this thing called the vertical line test. So if it touches more than once, it's not a function. If it only ever touches once, then we would call it a function. Okay? Now, horizontal line test will come into play later. It will help us to determine if a function has an inverse or is invertible, or if we have to put a restriction on the domain to be able to make it invertible. So it operates the same way as the vertical line test, in the sense that if it touches more than once, it's not referred to as one-to-one. So this is not one-to-one because it touches more than once. This is not one-to-one because it touches more than once. But this is one-to-one because anywhere I draw a horizontal line, it's only ever going to touch one time. All right. So functions come as modifications of what we refer to as base functions. So we have the constant function. This c stands for just some number. It could be 2, could be 4. What ends up happening is you just get a horizontal line at whatever that value is. So I just put a c here, and I wrote some fictitious number c, and I put my horizontal line there. F of x is equal to x, or the line y equals x. It's just the 45-degree angle line where each x value is equal to each y value. So you're looking at 1, 1, and then 2, 2, and then 3, 3, okay, and dot, dot, dot. The absolute value of x. All right, so this is going back to that idea where the absolute value has 2 possible paths that you have to look at. So you have to look at the positive path and you have to look at the negative path. So it's if your x value is bigger than 0, you just graph it like the line y equals x. So that's making reference to this half of it. But if your x is negative, smaller than 0, actually change the sign of it. That's what that negative means. So if you're at negative 2 and you're going to plug it into here, you think about it as, all right, well, what is the opposite of negative 2? Well, the opposite of negative 2 is positive 2. So this converts the sign to a positive. All right. Next one would be x squared, or the quadratic, and that's that U-shaped curve that you guys are familiar with. It has one turn, which is right here, and its degree is 2. And then we have the cubic, which has 2 turns, a turn there, and those 2 turns are here and here, and we have a degree of 3. And I want you to start to recognize that there's this relationship between the degree of a function and the number of turns that can potentially occur. Okay. Now we also have the function 1 over x, which is the reciprocal function. And it's asymptotic to both axes. It never crosses, it just keeps hugging closer and closer. And then if you square it, you get 1 over x squared, and it's asymptotic to the positive y-axis as well as the horizontal x-axis. We have 2 more base functions to discuss real quick. So you have the square root function, and the square root's only defined from 0 off to positive infinity. And so like 1 would be on it, 4, and then 2 would be on it, okay? And then we have the cubic, and we could have the quartic, or the fourth root, the cube root, sorry. And then a relation is a function. So we have to think about that definition. So anytime you do a bunch of ordered pairs, it's a relation. But sometimes relations are functions. So we're going to do this relation. We're going to go A, B, we're going to do B, C, and we're going to do C, C. And is that a function? Well, the definition says, for each element in the domain, there is one and only one element in the range. So does A, does B, does C, does each element in the domain have a place it's going to? Well, A is going somewhere, B is going somewhere, C is going somewhere. So that part of the definition is met. And it says one and only one. Okay? Well, if we graph it, we go, all right, here's A, B, C, and here's really, I should put an A there as well. Here's A, B, C. So A goes to B, B goes to B, C, and C goes to C. A has one and only one. There's not 2 above it, there's just 1. B has 1 and only 1. And C has 1 and only 1. So this is a function. So let me give you some examples to compare that to. We have the set ABC, and again the set BC, domain and range. Is this a function? Well, A doesn't go anywhere. And so the answer is no, it's not a function. Because A does not have a place it's getting mapped to. And each element of the domain must go somewhere, must get mapped somewhere. And then over here, you have A, B, C, and then B, C, and B is going to here and here. And since B is going to 2 spots, it's not going to be a function. So you can only go to 1 and only 1. You can't go to 2. Okay? So A could go to B and C could go to C. But B is going to 2 spots, not a function. Okay? Now, you're going to be asked to try and come up with ways to see if something is a function that's more graphical. And so I picked the problem where it says y is equal to plus or minus the square root of 1 minus x. And I'm going to say, well, take your graphing calculator and go to the y equals key and type in y1 the square root of 1 minus x. And then in the y2 spot, negative the square root of 1 minus x. And do make sure you've captured those in parentheses. Okay? And what you're going to have is some graph that looks like this. And if I throw a vertical line on there, it is not a function. Now, it is one-to-one. It only ever touches once on the horizontal line test. But to determine a function is the vertical line test, and that's not a function. Okay? And if you think about taking 0 and you plug it into those x's, 1 minus, so 1 minus 0 is 1, and then the square root of 1 is 1. And put the 0 here, you've got the square root of 1 being 1, but then you make it negative 1. And I just realized I graphed this wrong. This should be shifted over 1 unit starting here at positive 1. So correct that in your notes and make that shift over, okay? Now, you have to deal with this notation, this f of a plus h. And remember that college algebra is basically pre-calculus without trigonometry injected into it. So you're starting to get used to the idea of what a derivative is, but they're trying to just teach you how to operate the derivative. So if your function is 2x plus 4 and you're trying to find f at a plus h, what that's saying is you take what's here and you replace it with the a plus h. So whatever this thing is, and I call it a placeholder. We probably don't even need to write a letter there. We would just say f open space 2 open space plus 4. And whatever we put there, and here's the side we do the algebraic work on. So I'm going to say f at a plus h. Well, I'm going to plug the a plus h into that space. So I have 2a plus h plus 4, which is 2a plus 2h plus 4. Okay? Now, the actual slope formula that gets used, or one of the two, for the derivative is this, g of x plus h minus g of x over h. And then they apply this limit to it, but limit is a calculus idea, so right now we're just dealing with the algebraic side of it, okay? And we are told that our g of x is 2x plus 1. So, we're first going to get g at x plus h. Take the x plus h, put it in place of that gap. Okay, so the x plus h goes in here. Okay. Now, we're going to distribute the 2 and have 2x plus 2h plus 1. The second part of this says find g of x. Well, g of x is just 2x plus 1, so there's no work that needs to be done there. And now we're going to take this g at x plus h, and we found that to be this value. And we're going to put it in our ratio, and then minus, and then we have the 2x plus 1. Now remember, with the negative, we distribute it. Some people will say, convert it to a plus and make it the subtraction of it. That is correct. That's actually more correct than what I just did. And it'll go there, and then it'll go there. So now I have 2x minus 2x. They eliminate. They don't cancel. Canceling is 4 divided by 4. When they subtract, they eliminate. So 2h doesn't have a counterpart. The 1 minus the 1, they eliminate. So you're left with 2h over h. The h's cancel, which is 2. And if you'll notice, that's actually the slope of the function that you're working with. The slope of the function is related heavily to a thing called the derivative. And this part of the formula is heavily related to a thing called the derivative. So you're actually starting to scratch the surface of calculus with that. Okay? Hopefully that's helpful.